Is it visible? What about the problem? Have you completed the final step in this problem? I asked you to find out the surface temperature and steady state temperature. How many of you have completed it? Hello? Hello? Am I audible? Am I
Yes.
audible or not? Hey, speak,
Sir.
man.
Yes, sir. Yes, sir.
Are you there? All of you, physically present and mentally absent. Am I correct? Huh? See, if the attitude continues, see, I will be, I will be on Wednesday, right? On Wednesday, I will be giving you the first assignment, okay? And you are supposed to do it, and the assignment will be having many problems, okay? And individually, I will be changing the values, k values, etc. Okay, so each and everyone is expected to do the problem on their own. Okay, no copying, nothing should be there. Okay, uh, 1 minute. Hello, am I audible?
Yes, sir. Yes.
Yes,
Okay,
sir.
up to what step we did the problem on the day? Up to which step, ma? What are the things we found out on the day? Surface temperature is, I think we have found out. Am I correct? All of you are there or not?
Sir, I guess we have to find T naught, sir.
Huh?
I guess we are yet to find T naught, sir.
Surface temperature, center temperature, right?
Yes, sir.
Surface temperature, did we find out? Hello? Am I audible here?
Yes, sir. Yes.
Yes, sir.
Yes, sir.
What's
Yes.
happening, man? What's happening to you people? What's happening there? All of you are there or not? Kindly open your webcams.
Yes,
I want to
sir.
see you. I want to see you, man. See, it's ridiculous. Only one step I asked you to do, you didn't do it, huh? T naught is the center line temperature, center temperature, which you are supposed to find out, right? You
Yes, sir.
didn't do it. Huh. Surface temperature, have we found out? What is the value we got? Hey, all of you have got the problem with you or not, ma?
Sir, wasn't it 63.33 the surface temp?
Surface temperature we found on the day, right? Yeah, you can close your webcams. You can close your webcams. We have found surface temperature on the day, right?
Yes, sir. Wasn't it 63.33?
Okay. Then why you people are struggling? Did you have a notebook with you or not? Calculators, notebook. Now you are expected to find out the center temperature, right? So how to get the center temperature? I have already told you. You can use the expression, this expression. Okay. So this expression can be used to get the center temperature. Now we know that at r equal to 0, dt by dr at r equal to 0 equal to 0. So now what happens here is temperature at the center, T naught. Okay, T naught is center line temperature. We can have this expression to get T naught, or we can substitute, we can use the general expression. Central line temperature is it visible to you?
Yes, sir.
Yes, sir.
So this is the expression. Okay, is it visible? The expression is visible.
Yes, sir.
Yes, sir.
Yes,
Okay.
sir.
Now, since R is equal to 0, right? Since R equal to 0, this becomes 0. Okay. So totally what happens here is temperature at R equal to 0 is G R naught square. I used a QG, right? R naught is nothing but the outer radius. Okay. Divided by 4K plus surface temperature. Okay. So the QG value is internal heat generated value is what is the value we got QG on the day? Q suffix G.
2.68 10 to the power 9.
2.6 into
10 to the power
10
9.
power 9.
10 power 8 watts.
9, sir. 9.
10 power 9 watts. Okay. So we have QG. And outer radius, what is the outer radius? The outer radius is the length of the wire is given. Radius 2.5 mm diameter.
Yes, sir.
Okay. So the radius 1.25 mm. Okay. So now substitute T naught, which is equal to 2.6 into 10 power 9 divided by into R naught square 1.25 mm. All of you are listening or not?
Yes, sir.
Students, do you find any difficulty in substituting the values and getting the result? Any problem for you? Why none of you didn't do it? Why you want me to do all the problems? If this being the case, then you will not be able to get good marks in the CAT exam as well as FAT exam. Please understand that. And what is the surface temperature value? 63, yeah. How much?
63.33, sir.
63.33.
3, sir.
Okay. Now what is the central line temperature now? What is the value, pa?
So I'm getting 114.08.
114.08.
Yes, sir, that's what I'm getting.
Others, please check.
Sir, I got 114.11.
Yes, sir. 114 point.
Same, sir. Same.
What is the wall temperature you got, ma? All of you? Surface temperature?
Sir, I think
CS, sir?
surface temperature is 456.25, sir. Not 63, I guess.
What, man? What you are doing? Huh.
Sorry, sir. Confused with the previous problem.
Someone said it wrong, sir. Surface temperature is 456.25, sir.
Hey, what you are doing here? Somebody says 63, somebody says 456. Which one is correct answer?
456, sir. 456.
456.
456. Okay. 456
The
point
total value is coming around
25, sir.
25.
25 degrees. Okay, now what is this value?
507.03.
507.03. At least this is right or not?
Yes, sir.
Yes, sir.
Yes, sir.
So the central line temperature T naught is this one. Okay. So in this place, what happens is this becomes 0. I use this expression. This becomes 0. Okay. When this becomes 0, G R naught squared by 4K plus TS will give you. Okay. Surface temperature, somebody said 63. Somebody said 456. Okay. Please check it out. Okay. Because I'm not having the notes with me now. Okay. On that day, I have calculated the surface temperature also. Students, please improve your skills. It's very important. You have to improve your skills, or otherwise it's very difficult. Okay. So the central line temperature is 507.03 Kelvin. Okay. So this is something about the cylinders. Okay. So in the previous cases, we have solved problems with composite wall, cylinder, and sphere, right? Similarly, here also we solved problem with slab generation, right? Internal heat generation in a slab, internal heat generation in a cylinder, and finally the last one is internal heat generation in a sphere. Okay, so again, what happens is the outer radius it is given by capital R, and smaller is nothing but radius at any point from R equal to 0 to R equal to capital R. Is it fine? Students, is it visible?
Yes, sir. Yes, sir.
Yes, sir.
Okay. And the Poisson equation, we know that the Poisson equation for sphere, right? You may ask a question, sir, how come you got all these equations? Earlier you didn't do it. Okay. So this is the equation, ma. Okay. For Cartesian coordinates, we got this, right? Am I correct? Dou square T by dou
Yes,
square.
sir.
Okay. And how it becomes Fourier equation, how it becomes Poisson equation, and how it becomes Laplace equation. Everything you don't know. Sorry, everything you know. I'm sorry. Everything you know, right? Okay, if there is no internal heat generation, then the equation becomes Fourier equation. If there is internal heat generation and steady state, then it is becomes Poisson equation. And if there is no internal heat generation and if there is steady state, then the equation becomes Laplace equation. Am I correct or not?
Yes, sir.
Yes, sir.
Okay. Similarly, for cylindrical coordinates, we have this expression where G is nothing but internal heat generation, and rho Cp dou T divided by dou T is nothing but the energy stored in the element in the cylinder. Similarly, rho Cp dou T divided by dou T in case of sphere is this one. Okay. So when we include, when we neglect y and z axis, what happens is 1 by r into dou by dou r into kr into dou t by dou r plus g, which is equal to rho Cp dou t by dou t. And if it is steady state, then what happens is we will be having 1 by r dou by dou r into kr into dou t by dou r plus g, which is equal to 0. Okay. So we have to neglect this y axis, z axis, and steady state. Okay, for cylindrical coordinates. Similarly, for spherical coordinates, 1 by r square dou by dou r kr square dou t by dou r, we have to neglect this y-axis, and we have to neglect this z-axis, and we have to neglect this steady state. So when you neglect all these things, we will be getting this expression. Okay. So for radial systems also, I told you this equation. From this equation, is it visible at the top? This equation is visible.
Yes, sir.
Okay. So from
Yes,
this,
sir.
when we have steady state and when we consider only the x-axis, okay, we will be having this expression. Similarly, for sphere also, when we consider only the x-axis and we neglect y-axis and z-axis, okay, and if we assume steady state and if there is internal heat generation, then what happens is we will be getting this expression. Okay, and when we rewrite this, what happens is this minus g by k goes to the other side and this r squared goes to the other side. So the expression becomes d by dr into r square dou t by dou r or dt by dr, which is equal to minus gr squared by k. And what happens here is when we differentiate this, sorry, when we integrate this, when we integrate this, then what happens is r square dt by dr, which is equal to minus gr cube by 3k. We know that r square, when we integrate r power 3 divided by 3. Am I correct? When we integrate r square, am I correct or not, ma?
Yes, sir.
Because
Yes,
you
sir.
Yes, sir.
people, you are more experts than me, especially in mathematics. Okay. So r square, when we integrate, it becomes r cube by 3. Am I correct?
Yes, sir.
I mean,
Yes,
correct
sir.
or
Yes,
not?
sir. Yes, sir.
Okay, so what happens here is here r square dt by dr, which is equal to minus g r cube by 3k. Okay, plus c1. Okay, and again when we integrate, what happens is we will be getting t, which is equal to minus gr squared. So what happens here is we have to uh, divide this expression all the three by r squared. So this becomes dt by dr. This becomes minus gr by 3k plus c1 by r squared. Am I correct? When we divide all the terms by r
Yes,
squared,
sir.
Yes,
the
sir.
equation 1, all of you are able to understand how we got this?
Yes, sir.
Yes, sir.
Okay, and then again when we integrate it, we will be getting minus gr squared by 6k minus c1 by r plus c2. Okay, so this is the expression we get. Now we have to find out what is c1 and c2, and we know that dt by dr, which is equal to 0 at r equal to 0, and or in other words, what happens is the central line temperature will be the maximum temperature. And similarly, we also know that the heat conducted at the surface is equal to the heat convected to the surrounding atmospheric air or surrounding atmospheric fluid. Okay, suppose if the solid is dropped inside a liquid, then we have to take the convective heat transfer coefficient. Okay, so minus ka dt by dr, which is equal to ha dt or ha del t. Okay, and when we put those conditions, we will be getting the values of c1 and c2, and we will be getting the expression t equal to minus gr squared by 6k plus gr squared plus gr squared by 6k plus gr by 3h plus t infinity, where small r is nothing but the radius at any point and capital R is nothing but the outer radius. Okay, so that particular thing you have to understand. Okay, and for getting the temperature at the outer radius, we will be using this equation. Okay, so we will be using this expression. Okay, uh, G by 6k. G is nothing but QG, ma. Don't get confused with G. Okay. In all the textbooks, they used to mention G, but in my calculations, I always use Q suffix G. Okay. So uh, try to use Q suffix G. And I think this is in watt per meter cube. Am I correct, ma? 2.6.
Yes,
Hello?
sir.
In the problem, none of them they told
Yes,
me,
sir.
because it should be expressed in watt per meter cube only. See, units are very, very important, students, because finally, when you do the problem, you will be getting wrong answers. Okay, Q suffix G will be in watt per meter cube, whereas Q will be in watts. Okay, and heat flux will be in watt per meter squared. Please understand. Okay, Q suffix G, internal heat generated, will always be in watt per meter cube. So to find out the temperature, we will be having this expression T equal to G by G is nothing but QG. All right, it should be expressed in watt per meter cube divided by 6k into r squared minus r squared, where capital R is nothing but the outer radius and small r is nothing but the radius at any point from the center, plus gr by 3h plus t infinity. Okay, now what happens here is we know that uh, yeah. So from in this expression, you can see here dt by dr, which is equal to 0 at r equal to 0. So what happens is C1 is equal to 0, and by energy balance, heat conducted in up to the surface, which is equal to heat convected out. So from that we have got C2, and after substituting the C1 and C2, we are getting this expression. This is the final expression to find out the temperature. Okay, so please understand, students, and you may ask me a question, sir, what is the examples for this? Okay, so uh, yeah, an atom bomb or a small bomb which is in the form of a sphere can be taken as an example, or in some cases, okay, what happens is they used to mention um, uh, even the practical case, when you want to you can assume the apples, the oranges, the ripening of apple, ripening of oranges. Okay, there will be some internal heat generation in it. Okay, when it is exposed to the hot sun. Okay, there will be some internal heat generation. Okay, so the ripening effect takes place. Okay, that can be assumed as a spear. Okay, those apples can be assumed as spear, and we can find out. We can find out the surface temperature, and we can find out the internal temperature, inside temperature. Okay, students, and similarly, the that is the nuclear reactor fuel rods. Okay, the fuel rods, inside the fuel rods, you can have small shells which will be in the form of a sphere. That can also be taken as a sphere, and we will be having internal heat generation in that also. Is it fine? When we talk about
Yes, sir.
examples, is it fine, students?
Yes, sir.
Okay, even in Senjal, they have mentioned some examples. Okay, and yeah, can you solve this, or you want me? Because after solving this, I will be moving on to introduction to module 3, that is transient heat conduction. Actually, in module 2, we have this syllabus like this. So you will be having, for CAT, you will be having module 1, module 2 complete, and module 3, whatever I do up to next Friday, you will be having it. Okay, so in module 1, that is the general concept of conduction, convection, and radiation. Small problems will be asked, and similarly, uh, significant applications of heat transfer can be asked. Okay, in module 2, we have discussed everything: overall heat transfer coefficient, internal heat generation in wall, cylinder, and sphere, composite wall, composite shell, critical radius of insulation. Everything I have covered. And in module 3, we have unsteady state conduction, unsteady state heat transfer, which is the major thing we have to study. And then we have steady state heat conduction in 2D systems. Especially, this involves graphical and numerical methods. After discussing about unsteady state, we will be solving steady state 2D systems. Okay, so that is the order I will go. Okay, because after discussing about one-dimensional heat conduction in composite wall cylinder, and internal heat generation in one-dimensional cases, okay, if I go to two-dimensional, then it will not be easier to understand. So I will move on to one-dimensional unsteady state heat transfer. Then after completing that module 3, especially that these topics in module 3, then I'll move on to steady state heat conduction in 2D. Okay, then I will move on to module 3. This is the order in which I will be going. Is it fine, students? Is
Fine,
it
sir.
fine?
Yes, sir.
Okay, ma. Can you solve this sphere problem? All of you? Heat is generated in a solid or sphere of 10 centimeter dia at the rate of 600 watt per meter cube. So Q suffix G is given. The radius is given as 5 centimeter. Surface heat transfer coefficient is 10 watt per meter squared Kelvin. That is, H value is given. K value is given as 0.2. T infinity is given as 30 degrees C. So you are asked to find out the maximum temperature and surface temperature. All of you are able to do this, or you want me to do?
So can you do, sir?
Yeah,
Sir, we can do.
you can do. Okay, no
Yes, sir.
issues. No issues. Let me solve it in uh, 1 or 2 minutes. Please wait. So here, given data. See, the very first important thing is you have to write the data. So is it visible, ma, all of you? The question is visible
Yes,
to
sir.
you?
Yes,
Yes,
sir.
I
sir.
have
Yes,
copied
sir.
and pasted. Okay, the given data. Please write the maximum radius R is 5 into 10 power minus 2 meters. Okay, so the diameter is given as 10 centimeter here. Okay, so I have given it as, okay, and similarly Q suffix G is 600 watt per meter cube, and H value is given 10 watt per meter squared Kelvin, and K value is 0.2 watt per meter Kelvin, and what is the other thing? T infinity is given. These are all the things which were given, right? 30 degrees C. Am I correct? Any other
Yes,
data
sir.
given? Okay, now you are asked to find out the maximum temperature and surface temperature. Okay, so maximum temperature and surface temperature. We know that the surface temperature Ts will be at the surface temperature will be at r equal to small r equal to at the radius. So the surface temperature will be equal to, so the first term will become 0. Am I correct or not?
Yes,
Yes,
sir.
sir.
Hello. You will be having gr by 3h plus T infinity. So that will be the expression. Let me check it out. Yeah.
Sir, 1 second. Can we show the problem?
You solved it, huh?
No, sir. No, sir. I want to see the question.
Yeah. Let me write the expression. T equal to g by 6k into r square minus r squared plus gr by 3h plus T infinity. So at surface temperature, you are asked to find out two things, ma. Is it visible, students, all of you? Is it visible?
Yes, sir.
Yes, sir.
Yes, sir.
Yes, sir.
You are asked to find out the maximum temperature and surface temperature. Okay, so the surface temperature, at surface temperature we know that small r which is equal to capital R. Am I correct? This
Yes, sir.
expression is for temperature at any point r. Temperature at any point r is this expression. At surface, capital R, at surface, capital R equal to small r. Okay, so what happens is the first term goes out. So T equal to, this term becomes Qg divided by 6k into r square minus r squared. So this becomes 0. Okay, am I correct? Am I correct
Yes,
or
sir.
not? Okay, so
Yes.
finally we will be having only these two things. Okay, so this becomes 0. When you substitute the values, 600 into outer radius. What is the outer radius, ma? 5 into 10 power minus 2. 10 power minus 2 divided by 3h, 3 into 10, plus this value, T infinity. What is the surface temperature surrounding
30
fluid
degrees
temperature?
Celsius.
30 degrees C plus 30 degrees C. So that is the first answer. Surface temperature, T surface. Okay. I use this equation, ma. All of you are able to understand. This
Yes, sir.
becomes 0. Only
Yes,
we
sir.
will be having this term. So how much it is?
31 degrees Celsius. Sir. 31 degrees Celsius.
31 degrees C. Okay. Now find out the other thing. What is the other thing? Maximum temperature. So the maximum temperature will be at the center, right? So now this is also included. This is 0. This is 0 at TR equal to 0. Then you will be having expression Qg by R squared by 6k plus Qg R by 3h plus T infinity. You have to use the same equation. Only thing is here the small r becomes 0 and you have to substitute the capital R. Capital R value we know that 5 into 10 power minus 2 meters. Is it fine?
Yes, sir.
Whether you can do it?
Yes, sir.
Sir, which one?
So 32.5, sir.
32.5, is it correct? Maximum temperature? I think I have given it in the slides also. Okay, if you want to have doubt, 32.5, is it correct?
Yes, sir.
So for sphere, this is the expression: temperature at any point R, G by 6K. G, see, generally they used to use G, ma. I used to use Q suffix G because G and all, it will be slightly confusing. Okay. In some textbooks, they used to G, and in some textbooks, they used to have Q suffix G. Okay. So generally, I used to have Q suffix G because heat is usually mentioned with the letter capital Q or small q. Okay. So generally I use that. Okay. So the maximum temperature is 32.5 degrees C when you use this expression. And for surface temperature, R equal to small r equal to capital R. So this first term becomes 0. So you will be having only GR by 3H plus T infinity. Is it fine, students?
Fine, sir.
Is it fine?
Yes, sir.
Shall I move on to the next topic?
Yes, sir.
Yes, sir.
Okay, sir.
Is it fine, ma? Shall I move on?
Fine, sir.
All of
Yes,
you
sir.
have copied it.
Yeah.
Yes, sir. Copy.
And see here, this step, what they have mentioned is they have not mentioned r square minus 0, small r equal to 0. Okay. They have indicated it. Fine. Therefore, putting r equal to 0 in the above equation. So it becomes like this. Okay. Okay. So all of you have taken this? Everyone?
Yes, sir.
Yes, sir.
Yes, sir. Take it.
Okay, ma. Now the next topic is in transient condition. Okay, in module 3 we have, as I mentioned earlier, we will be having studying unsteady state heat conduction, one dimensional. Then I will go for steady state heat transfer, two dimensional thing. Okay, is it fine? Is it fine,
Fine, sir.
students?
Yes, sir.
Okay, so now what is the thing which is shown in the diagram? Can you tell me? Uh, What is unsteady state? What is steady state? From the diagram, can you tell me? What is unsteady state heat transfer? What is steady state heat transfer?
So first one, steady state.
Okay.
The copper bomb.
Ah,
The roast beef is unsteady because there's a different layer of temperature.
okay, very good. See, steady state temperature is the one, steady state heat transfer is the one where the temperature variation doesn't change with respect to time. Okay, unsteady state heat transfer, automatically there is increase in temperature or decrease in temperature, okay, with respect to time. Is it fine? Is it fine,
Yes, sir.
students? Okay. Now, what happens is usually all the heat treatment process, we know that the heat treatment process were conducted mechanically to improve the strength of the material. Am I correct? Am I correct or not?
Yes, sir.
Okay.
Yes.
Now, what happens here is you have all the process for since see, food industry. I already told you it uses the heat transfer technologies to the greatest. Okay, but you people, you don't like that being mechanical engineers. Okay, let me quote the example of uh, most of you or some of you have the experience of visiting integral coach factory where the coil springs, right? The coil springs, after getting it out from the hot furnace, it is immediately quenched into cold water. What is the reason for immediately quenching it into cold water, ma? What is the immediate? What is the reason for immediately quenching the hot coil spring into cold water? All of you are there.
Sir, is it a hardening technique, sir?
It's a hardening technique, or the heat is transferred from the hot coil spring to the surrounding fluid. Okay, am I correct?
Yes, sir.
Yes, sir.
Okay, and the heat transfer rate is very much higher because the convective heat transfer coefficient of the liquid is very high. Am I correct?
Yes, sir.
Am I correct? Am I correct or
Yes,
not?
sir.
Ma?
Yes.
Okay. Suppose if the coil spring is allowed to cool in still air, right? To achieve the temperature of the surface to the surrounding temperature, how much time will it take if it is cooled in still air?
Sir, it'll take a lot of time, sir.
It will take a lot of time. Why? Why, ma? Because the rate of cooling to the still air is lesser, or in other words, air will be having very less convective heat transfer coefficient. We have already studied this. In the very first topic, we have studied this. We have discussed this. Am I correct?
Yes,
Yes,
sir.
Don't
sir.
know.
Yes, sir.
In composite systems, the very first slide says about this. See, try to remember, ma. Heat transfer is very, very important subject, ma. I don't know why you people are not studying it properly. So this is, yeah. This slide, is it visible to you?
Yes, sir.
See, look at the H value. H value for gases is 2 to 25. For liquid, 50 to 1000. And if it is forced convection, then it is 50 to 20,000. Am I correct? Is it correct?
Yes, sir.
So that's where if you allow the, sorry, if you allow the hot solid to cool it in still air, right? The convective transfer coefficient of air is lesser, whereas the convective transfer coefficient of the fluid is higher, right? So that's why when we go for heat treatment techniques, okay, immediately we will be dropping the hot solid into the liquid, which will be at a lesser temperature. Cooling of hot metal forging. Okay, so the initially the hot metal will be at a temperature of 200 to 300. The water will be at a temperature of around 30 degrees C. So what happens is you will be having the cooling of the hot solid to the room temperature in in a few minutes time. Okay, it will take some few minutes time, but still the outer surface may be cold. Okay, but at the center there might be some hotness. Okay, so it's not compulsory that it's not compulsory that, okay, the whole solid attains full temperature, room temperature. Am I correct or not? Or the liquid temperature in this
Yes, sir.
example? Okay, so the inner surface, it may be at a slightly higher temperature, and there comes the thermal conductivity of the material, right? And there comes the thermal conductivity out of material. So when we want to study, and since I have given this roast meat also, nowadays you people, you have this that OTG, and you are going for grilled chicken and all. Okay, so the heat is transferred, right, to the meat piece. Okay, so that what happens is you will be having a so when it is exposed, right, when the meat is exposed to that particular temperature over a period of time, slowly what happens is it gets roasted, and then you will be after some time you will be taking it out, and you will be getting the desired taste. Okay, so that's what happened in case of OTGs. Okay, OTGs are grill, what are new terms? I don't know about the new terminologies, whatever you say you use. Okay, so that is one particular thing which you should understand, the exposure, right? And this is what happens in case of hot furnaces also, right? In case of hot furnaces also, when you insert a rod, okay, in a hot furnace, initially it will be at a lesser temperature, and what happens is when the material goes inside, what happens is it increases, or that there is rise in temperature. Okay, so two processes are there. Cooling process is also unsteady state, comes under unsteady state heat transfer. Heating process is also comes under unsteady state heat transfer. Okay, so especially in food industry, as I mentioned earlier, we are using this technology to the maximum thing. Okay, and similarly in case of mechanical industries, especially radiators, car radiators. Okay, in case of car radiators, what is the purpose of using radiator, ma? Anyone? What is the purpose of using radiators?
Sir, it's a
Students,
cooling system, sir.
cooling
For
system.
car.
Okay, so the quantity of heat dissipated, the quantity of heat dissipated is slowly, that is the quantity of heat generated inside the engine cylinder. It has to be, some portion has to be dissipated to the surrounding atmosphere. Okay, so when we have air cooling in case of single cylinder engines, the cooling is very slow, right? And when we go for multi-cylinder engine with higher heat capacities, for example, three-cylinder engine, we have 1000 cc, 2000 cc, 1500 cc cars, etc. Am I correct?
Yes, sir.
So the heat energy developed by those cylinders is very higher. Okay, so some portion of the heat energy has to be dissipated, or otherwise it will lead to the expansion of the piston material, so that what happens is the piston won't reciprocate inside the engine cylinder. Okay, so again the concept of heat transfer comes there in case of car engine cylinder design. Okay, so the selection of material, the material having higher thermal conductivity, lower thermal conductivity, etc., low heat rejection engines, everything. Unless you know the knowledge about heat transfer, or you don't have the idea about heat transfer, it's very difficult. Okay, so some portion of the heat has to be dissipated. So in case of two-wheeler engines, the engines were smaller size, so air cooling is sufficient. Whereas in case of four-cylinder engines or three-cylinder engines, the heat energy which is generated inside the engine cylinder is very high, so that we have to go for water cooled ones. Okay, and as I mentioned earlier, the liquids will be having higher convective heat transfer coefficient, so that it can take more heat energy when compared to the air. And one more thing, students, that's why the liquid sodium is used as a coolant in power plants. Am I correct or not? How many of you studied that liquid sodium cooled heat reactors, liquid metal cooled fast breeder reactors? Did you studied in power plant engineering, students? Have you studied? Students, am I audible or not? Did you study
Yes, sir.
power plant engineering technique subject?
Yes, sir.
Yes, sir.
In power plant engineering, did you studied about liquid metal cooled fast breeder reactors? LMFBR? Say yes or no, man. You didn't study. Hello? Am I audible?
Yes, sir.
Yes,
sir.
So why the name liquid metal cooled? Because the liquid sodium will be in liquid state even at very high temperatures, and it is capable of absorbing more heat energy. Okay, so that is one. See, these are all some of the examples for unsteady state heat transfer. Okay, and now when we talk about unsteady state heat transfer, we know that the heat energy which is convected to the from the solid to the outside is equal to the increase in the energy of the body. So it may be increase in the energy, or it may be decrease in energy, depending upon whether the process is heating process or cooling process. Okay, and when we integrate it, okay, we will be getting this expression: the temperature at any point at any time t minus the surrounding temperature divided by the Ti. Ti is nothing but the initial temperature, and M is nothing but the mass of the body, volume, V is nothing but the volume of the body, and rho is nothing but the density of the body. So now the heat transferred, right, from the solid to the uh, heat convected, okay, to the um, liquid is equal. It is by means of energy balance, they used to assume it as equal. Okay, and using that, they have this expression Ha del T, which is equal to mcp dt. You may ask a question, sir, how come the small dt has come? See, actually it is nothing but Ha dt, or Ha into t as t infinity minus t, which is equal to mcp dt divided by small dt. Okay, so this dt has gone to the other side. Okay, so don't get confused. Okay, the heat convected is equal to the increase in the energy of the body during a small time dt. So small t stands for time and capital T stands for temperature. Okay, and you will be getting this expression. Okay, you will be getting this expression since T infinity is a constant. Okay, anyway, I will discuss this tomorrow also, and I will discuss about this effect of this B value also. Okay, anyway, I will discuss about this in the tomorrow's class also. Let me stop the recording.
Sir, you haven't shared these slides yet.
Yeah,
The
yeah.
model view.
Today I will do it, ma. Today I will definitely do
Okay.
it.